Hello, students. Got another email with some questions. This time, let me see it here. Looks like these are MCs out of 11.1. So let's take a look at the MCs for 11.1. I do have to come down here and move to the next page. One more page. Okay, 11.1 MCs. Let's see here. Question 6. Question 6. Answer each of the following. How many lines can contain a particular segment? Okay, so this is similar to what we did in class. If I want to include that exact segment, right? How many lines can contain that entire segment? And when you think about it, to include the segment, you have to include the points that are on the segment. And once you include 2 of those points, you create a unique line. So that's why the answer for 6A, let me zoom in just a little bit. That's a little small. For 6A would be 1. Okay, so that one seems pretty, maybe you're like, okay, that makes sense, Scott, I totally get it. Okay, so now how many rays can contain a particular segment? Okay, so now how many rays could contain a particular segment? Remember, only one line could contain the segment. So if I say, here's my segment A, B, this is my segment, I want a ray that contains that. Well, remember, this is part of a line. The line continues on to infinity, but I only want that red part to be included. Here comes the fun. Pick a point to the left and then choose that ray going to the right. It will include the AB part. So that's 1. Now pick a point to the left of D, or left of C. Here's D. Guess what? This ray also contains AB. Pick one over here. I get E. So how many points can I pick going that direction? Infinitely many. And I still haven't even gotten over to the other side for a point over here that could go that direction and conclude and contain AB as well. So how many rays can contain a particular segment? Infinitely many. And how many planes can contain a given line? Well, just think about that. Take that line, for example, right? Think of this line. And like we did in class, like if that line is the wall, like where the wall and the ceiling meet, yes, you can already see there's 2 planes that contain that line. But if that ceiling plane started to tip at an angle and rotate, you could be like, wow, there's so many that I could create, so many planes that would go through that line. And once again, that would be the infinitely many. And is it possible for 3 points to be non-coplanar? That is a great question. Interesting. That's almost like an always, sometimes, never, right? It really is. Is it possible? And you can say it's always possible, sometimes possible, and never possible. So let's see here. 3 points to be non-coplanar. So again, think about what you're thinking about. Take 2 points. We know a line contains those 2 points, right? Maybe. Now pick a point that's not on that line. Why? Because from what we said in part C, there's infinitely many planes that would go through that line. So pick something to be like, okay, let's challenge ourselves. Let's pick something point C that's off of that line. Well, here's what's great, right? Then C and A are 2 points. They make a line. And B and C are 2 points, and they make a line. And if you can look right here, what have you just created? You've created a surface, which we can think of as part of a plane. And therefore, no matter how bad you try, no matter where you pick that point, here's my line. It's created by this pen going infinitely in both directions. Pick any other point in space. From these endpoints, I can create lines. Those lines and this will create a surface, a 3-dimensional surface that is known as a plane. So is it possible for 3 points to be non-coplanar? You could look at that and say, no matter how hard I try, it ain't going to work. Okay. So great question there. Let's go to number 7. Oops, too fast. There we go. Number 7. Given a line and a point that's not on the line, explain why there is only one plane containing the point and the line. So again, that links back here to what we just did in number 6 a little bit. So this one was 3 points. All we're doing now is saying take 2 of those points and make a line. Now I have the line, pick a point that's not on that line. This is about your explanation. Okay. Could there be another plane that contains the point and the line? And the answer is actually no, because any plane that contains the point and that line contains all the points of that plane. So there would be one, we would say one unique plane. And you could say, well, this is the same plane. Well, that's cool. We could say that all night and day, but it's not, not that a distinct or different plane would be in there. So yeah, there we go. Think of the argument. If you remember, if you just have the line, you could think of like tipping a plane through that line, and you have infinitely many of those. So just tip it until it hits the point that you're thinking of. And there's the one. That's it. Okay, let's see here. Question 12 came up next. And let's see, do I need to flip pages? I think I need to flip pages. Oh, here it is. Yep. Ranger. Ah, yes, forest rangers. Oops, let me get my drawings off of there. That might cause some problems. Forest rangers use degree measures to identify directions and locate fires. In the drawing, a ranger at Tower A observes smoke at a bearing of 149. And again, this is a bearing from north. So go 149 degrees from north. While another ranger at Tower B observes the same source of smoke at a bearing of 250 degrees clockwise from the north. So if you were picturing this, then let's come over here and draw it. So again, draw north in. There's north. Here would be 180 degrees from north. They did it at 250. Now again, 270 would be over here. So 250 is something like this. So this would be 250 degrees all the way around. Okay. So choose two locations for this. Use the bearings, a protractor, and a straight edge to locate the source of the smoke. If you don't have a protractor, I will give those out in class. I forgot to give them out in class before we left. Dang it. That's on me. So I forgot about that. But I did make photocopied ones that you can use at home. And then you can identify where it is. Okay. And a straight edge looking. Explain how the Rangers can find the location of the fire. Well, what you've got here is you've got two pieces, right? You know where this tower is, you know where this tower is. And so really what's great is where those two lines, the red line and this green line, where they intersect, that is the location of the fire. So in a sense, we're kind of creating, if you will, from the tower to the tower to the fire, we get something that's known as triangulation. And that's why I need just 2 points where each of those points points in a particular direction, and I can do what's called triangulating the position. It used to be used a lot in movies as like a fancy way to say, oh, how are we going to find them? I'll triangulate their position. But I mean, that's all it is. Okay. And this is for forest rangers and fires. What's interesting is that we also use it now. A lot of times we can use it with signals. So any signals, what we used to think of as radio signals, but now we have cell phones that are kind of giving off these signals. And so if a signal is being if a signal is being given to two different towers, kind of at the same time, what you can do is you can actually use those cell phone towers to try to figure out exactly where that person is located, right? And again, what we're saying when we say triangulate is these towers are fixed. So if I know how long it takes a signal to get from one of them, it creates, if you will, kind of like a circle around them. I don't know if I have a circle tool. Oh, I do. Is that going to give it to me? Oh, that's horrible. Why does it do that? Okay, let's pretend. I'm going to try to make this, I'm going to try to make this work out perfectly. That's horribly done. Okay, that's a little bit better. Okay, so picture this radio tower, like the cell tower, as like the center of a circle. And so when it gets this direction, it knows kind of how fast the signal is traveling, if you will. So it knows where someone is kind of on this circle, which doesn't do a lot because if you look at it, there's like infinitely many places they could be. And so then all you do is you bounce it off one other tower and you get something like that. And we'll paste that one in there. And now I need this circle to be at the center, but then I need to shrink it down a little bit. Right. So I have another circle. And then what that does is it actually tells me something which is interesting, but maybe not perfect. And that is that the person could be located here or here. So there's actually two locations they could be as I do that. So when we get to things like this, sometimes we need more than that. What's great about the towers is that they're all facing one. We launched them off of a particular direction. With cell towers, there's no guarantee that the person's kind of facing north all the time. So cool. There you go. There's that. Okay, I think that's kind of a cool one. Let's see here. What else do we have? Tower B get a different degree than Tower A. Yeah, so I think the big piece is you do have to make your drawing look similar to this. If you make your drawing too much different, you actually won't get the result. Like it'll look like they never do intersect. So you have to pick Tower A, like somewhere like this, and then go down here and make your angle 149 degrees and draw this line. And then Tower B has to be located somewhere up here. If you pick Tower B right down here, they wouldn't get an angle of 249 degrees from north. It wouldn't be this angle. Wherever the fire is, it has to be on this line. And so their angle would be more like maybe it's 10 degrees or 20 or 30 or 40 or 50. So that's why up here they actually are trying to say you've got to make sure you put your point up here. So pick a point up here wherever it is, and then from north go 250 degrees and go 250 degrees, and I guarantee you those two lines will hit if you draw your point in this part of the region. Yep. Okay. So again, when someone is standing here, what's great, this is north, right? Doesn't do anything but just kind of give you a guide for your directions. And the guide to the directions allows us to kind of come down here and say, okay, person A, the person who's in that like this tower is saying, I know I see smoke and it's in this direction. That all you did is you just created a ray, and the fire could be anywhere along that ray. In order to lock it down, we need some other component. And once again, we see this person over here is like, hey, it's along my ray going this direction. And so all we need to do is look at a map, make those two pieces, boom, we can see exactly where that fire is, and we can get the crews out to that spot as quickly as possible. So I mean, all of this is great, and they do say forest rangers do use this. Lately, at least in some of the areas, they're starting to use satellite technology. So satellite is constantly there taking pictures, which is great. Because forest rangers, if it's bright, sunshiny, clear skies, they can see quite a ways, and they usually make these towers up in such a way that they have good optics. But the issues are, well, of course, if it's cloudy or if it's foggy, they can't see it. So then they have to rely on different technology to kind of figure out where forest fires would be located. But anyway, I know historically this has been one of the main ways that we would actually figure out where forest fires were. Okay, let's see here. We got number 14. Let's take a look. So this one's definitely on the next page. 14. Mario was studying right angles and wondered if his math class minute and hour hands ever formed a right angle. Ah, okay. Yeah, so this is similar to in that I gave you a packet that had some clock arithmetic where we were coding and uncoding and decoding, and then there was one page about clock geometry. And so I think maybe I'll open up that page. Let's see here. Canvas. There we go. Jump in here. Where do I want to be? I'll just go to Scott's Solutions. And this was clock arithmetic activity. So on the clock arithmetic activity, there were problems at the end that were kind of similar to this. So these were with ratios and proportions. So it was 4:15. What angle do the minute and hour hands form? After 4:15, when do they form the next 90-degree angle? Taylor Swift, she's thinking about minute and hour hands forming a 90-degree angle, exactly like this person was. She ended after 2 o'clock, but before 2:30. After 3:15, but before 3:45. So again, a lot of components that could come into it. And the reason is when you look at a Clock with hands. When you look at what's happening with this clock, I wonder if there's one that I can adjust. I'm not sure. Interactive clock. Is this it? Maybe this is interactive clock. All right, there we go. So what you can see is as I move this hand forward, this is actually pretty good. As I move this hand forward, this is known as the minute hand. You can see it moving, right? But what's happening is the hour hand is also moving. So at 6:30, those hands don't line up perfectly. So one of them has moved halfway around. The other has moved halfway between 6 and 7. Okay, and that's why that activity we did in class with creating the angles was kind of useful here. If you have 12 points, you are making 30-degree angles. Okay, so 30 times 6 would give you 180. One hand has moved 180 degrees. The other hand has only moved halfway between 6 and 7, which would be 15 degrees. So originally, this hand was straight up, and it came down here, and now it's 15 degrees. So while the original angle between these hands was 180 degrees, you can see that every minute that amount is shrinking. And somewhere over in here, it looks like they get to be about 90 degrees. Okay. And so what's great is right now it requires that I only go to the minute. So for this interactive clock, only thing I can do is go to the minute. But truly, a clock would actually smoothly move between 6:15 and 6:16. It would kind of smoothly move. Doesn't just jump all at once. If it is smoothly moving between, then we could actually figure out exactly where you get 90 degrees. Okay, so let's go to where this person is, which is something like this. Let me make sure I get the question right. Class meets from 2 p.m. to 3 p.m. Is a right angle formed? Okay, so let's take a look. So 2 o'clock, so right here, it's a 60-degree angle. And I can tell that because the hour hand is at 2, which is 2 ka-chunks away, and each ka-chunk is 30 degrees. That's what that hand tells us. Okay, so now if I go forward, so that's 30 degrees. If I start this clock, actually the angle gets smaller and smaller and smaller. Okay. And eventually, if I go all the way around, I'll get to 3 o'clock. It does form a 90-degree angle at 3 o'clock, but class ends at 2:50. Okay, so I got to do something between that. So class ends here at 2:50, and that's definitely not 90 degrees right there. Okay. Somewhere they form 180 degrees. That's great. It's another good question. When would they form 180 degrees? But somewhere in here that looks like they form like a 90-degree angle. So what we probably want to do, at least what I would do if I was you, is you could take a look at the key to that sheet if you wanted to, because I did provide you step by step on how to get through problems like this. Or you could say, wait a minute, Scott, I know this hour hand right here. Let me go a little bit thicker on that. I know this one right here is great. That's my hour hand. My hour hand is moving. And it takes an entire hour for it to go that far. That's 30 degrees in 1 hour, which is 60 minutes. Okay. So let's cut out some nice things and we'll just say, well, that means it's going in 1 minute. That means it's going half of a degree, right? Just divide all of them by 60. Okay. So every minute it's going half of a degree, right? So after 20 minutes, you know exactly where it is. After 30 minutes, you know exactly how far it's gone. Okay. After 30 minutes, if you look at it, 30 minutes, that's half of this time. It'd go 15 degrees. That's for the hour hand. Now let's take a look at the minute hand. And we're going to have to do a little bit of math here. There's the minute hand. It's going straight up and down right now. That one goes all the way around in 1 hour. So it goes 360 degrees in 60 minutes. Let's divide those by 60 as well. So we maybe can do something about, let's go by the minute. and that would be 6 degrees in 1 minute. Okay, 6 degrees in 1 minute for one of them, half a degree in 1 minute for the other. Now we know if we did this and we did the red minus the blue, red minus blue would get me 60 degrees right now. So that means the red hand has a 60-degree head start. Okay. Now the blue hand has to catch up and it has to go past it in order to get ahead. So what I want to do is I want to take the blue with no head start. So 6 degrees per minute. I don't know how many minutes I need, but I know it's going to get down over somewhere in here. Okay, something like this. And then, so that's going to be kind of, it went past it. So the angle it travels would be from the 12 down to like the 5. But that's not the angle I want. I want the angle between the hands. So I need to subtract the red hand. And the red hand, we said, is going to be about half a degree per minute. But don't forget, it got a 60-degree head start. And at the end of this, I want to get a 90-degree angle. Again, you can put in whatever angle you want here. Just start from the picture, because if it said, does it ever form a 60-degree angle? The answer is it forms a 60-degree angle at exactly 2 o'clock. And then it'll form the next one, when the hands are, something like this. Okay, so there's one right around 2 o'clock, and then there's one around 2:20-ish. Okay. So this is what you want to create. And once you have this created, you can actually go and figure out exactly when that happens. So I do have to kind of distribute a little algebra here. Okay. So 6m minus 0.5m minus 60, that has to equal 90. So I'll combine my like terms and I'll bring the 60 to the other side by adding 60 to both sides. And let's see what we end up with here. So 6 minus 0.5, so that gives me 5.5 m's equals 150 degrees. And then just divide, this is just the algebra, right? Divide by 5.5. And there is m. And that is how you do it. So what is m equal to? M is equal to 150 over 5.5. Let's see here. I don't like fractions and decimals mixed. I think that just gets kind of crazy. And these are minutes. These are both degrees. So the degrees are going to go away and I'm just left with minutes. So let's see here. Let's multiply both by 10. Okay, there we go. Okay, and then let's see, I can divide by 5. So that gives me 300 over 11. Okay, so it's 300 elevenths minutes. Okay, so now this is where I get to use what we did in Math 105 and convert this back to a mixed number. Let's see what we get. Okay, mixed number. So 300 divided by 11. Okay, so that gives me 27 whole minutes. 27 minutes. And then 0.27. Okay, so let's just hold on for a second. We know this is like long division, so we could get a fractional or a remainder at the end. So let's just go back and say 300 minus 11 times 27, and I end up with 3. Okay, and 3/11 minutes. So 27 and 3/11 minutes would be one way to look at it. Now let's go back to the clock and see if that makes sense. Okay, so let me erase all the stuff off the clock face just so we can kind of see just the clock face here. Okay, so now let's grab it and drag it around. We want 227. Okay, so look at that angle. That angle is pretty close to a 90-degree angle, but if it's just right at 227, it's not exactly 90. It's a little bit shy. It needs to go just a little bit further. This is too far. 228 is too far. It's 227 and then a little bit more. 3/11 minutes. Okay. Now, if you really wanted to be accurate, you could actually figure out exactly how many seconds that is, which I know seems strange, but that's what it is, just a measurement of time. And this is where you could do a little tiny bit of conversion because we know there's 60 seconds in every minute. So we have 27 and 3/11 minutes. So we take that fraction and say, well, 3/11 times 60 would get me into seconds. Okay, so here we go. Multiply that by 60. 3 times 60 gives me 180. So this becomes 180 elevenths. Okay. So now I take 180 and I divide by 11, and that gives me 16. So I have 27 minutes and I have 16 whole seconds and then 0.3636. Okay. So I need to turn that into a fraction. So I'm going to subtract by 16 and then multiply by 11 because that's the cool thing we learned in class. And that would be in 4/11 seconds. So what time? At 2 o'clock. So at 2:27 and 16 and 4/11 seconds would be the exact time that this thing hits. So there you go. That's it. Phew. If you, let's see, what else could you have done? I would have accepted. So 227 as 16 point, whatever this 36 repeating. You could have put it that way as well. I would have taken that. Either one of those. That is, so does it make a 90-degree angle? It does, and you can determine the exact time that it does. And let's see here, and it says determine the nearest second. So there you go. There's the nearest second, and we can actually get better than that. We can determine the fraction of a second. So it looks like it's a little bit over, maybe a third of a second. And there it is. So do I like that kind of question? Yeah, I like that kind of question. Yeah, I really do. Because one, it includes geometry, it includes movement, it includes converting units, and it includes algebra. So what a great question. All right. And then I asked you to do a group work one. And again, you absolutely can do this group work with someone else, but it means you have to actually go and construct these. So let's see here. What would that actually look like? Let me see if I can sketch it out. I'm going to try sharing. I know they got this new whiteboard that I don't really like, but let's see if it lets me. No! I have no idea if this is even sharing right now because I want the old whiteboard back. Okay. I'm gonna try using it because all the tools are different, but okay. Let's try this because why not? So what you need to do is create a triangle that has a 30-degree angle, I think. Was it 30? What do I need? A 30-degree angle and a 50-degree angle. Okay, so here we go. 30-degree angle and a 50-degree angle, which means if you can add those up, right, you get 80. So the other one's going to be 100 degrees because it's going to be a triangle. Okay. Now, if you're actually building this, like get a piece of cardstock or at least, construction paper, something kind of heavy, and draw a line on it. And then using your protractor, measure up 30 degrees and then kind of just draw a line and let that line just keep going as far as you want. Come over and start another point somewhere and say from that point, I want to go 50 degrees. Okay. So whatever you get here, that looks more like 90. That's a little bit more like 80. So let's see here, 50 degrees, 45. So here's 90, 45 would be down the middle. So 50 is just a little bit more now. Okay, so something like this. Okay, there you go. And so make this angle over here 50 degrees. Then this one up here would be 100 degrees. And then go cut this out. Like actually cut this out so you have this three-dimensional shape. Okay, so now what could you build with this shape? Well, honestly, you can build a lot of cool things. So all you need is a line, and then you would take this shape that you've cut out, and you could put your shape right up against that line, right? And you could build a 50-degree angle by rotating your shape around. There's a 50-degree angle, right? You could also build a 30-degree angle, right? Because just twist it again, start from the same place. But if you just built a 50 and a 30, what else did you just build right here? 50's big, 30's small. Guess what? You just built yourself a 20-degree angle. Yeah, I know. Okay, so now if you just built yourself a 20-degree angle, that's fantastic, right? You could you could go back, pick your triangle up. Now that you've got these lines kind of drawn, put your 50 right next to it here. Actually be a little bit over here. You'd say 50 right there. 50 plus the 20 makes a 70-degree angle. Yeah, you can do a 70-degree angle. I know. I know. That's kind of cool. And so then if you have a 20-degree angle and you're 30, put your 30 on this line right here and draw back 30-degree angle. So put it so your 30-degree angle is down here. So this one is now 30, but the inside one is 20. You have a 30, you have a 20. Guess what angle you just created in the middle? And it'd be this tiny little piece right here. It would be a big 30 and a 20. The difference would be 10. So I just built a 10-degree angle. So with this angle that I have right here, you've got to be kidding me, but it's amazing. What can I do? I can build a 30-degree, a 50, and a 100. Those are the freebies. After that, what I can build is, what is it? A 20-degree angle? A 10-degree angle? Yes. With that 10-degree angle, I could put the 30-degree angle down here. 30 plus 10, grand total. I can now build a 40. I can build a 50. I can build can I do a 60 somewhere? Oh yeah, put a 30 and then put your 30 right next to it. Build another one. There's your 30 again. Just draw a line. Boom. So that cardboard triangle that you cut out, you can build a 10, a 20, a 30, a 40. We saw that. 50, 60, which is just two 30s, right? 70, which is the 20 plus a 50, gives you 70, right? Or take the 10 and do 30 and 30. That gives you 70. You can build an 80. Why? Because look at your 100. Your 100, the line continues. This angle next to it has to be 80 because they're supplemental. Or do the 30 plus the 50. Line up a 30, put a 50 down. Could you do a 90? You could do a 90. 90 is just a 30 and a 30 and a 30. Put those together. Okay. Or take the 10-degree, line your 100 up on it and brack your 100 off. The difference overlap is 10, so that leaves you with a 90 behind it. So I can do 90. That means I can do 100. If I can do 100, I can line 100 up on the 10 and make 110. I can make a 120. Yep. How? I can build a 50 and then I can just, I have the 50 built, right? So I put the 50 with the 20 and do it twice. That gives me 120. Okay. And I'm not so sure I'm not so sure how else to show this because it doesn't let me really rotate that piece. I need a document camera almost. I don't think I have one of those handy. Anyway, so that's, what else could I do? Okay, hold that thought. Hold that thought. I've got an idea, but I just need a piece of cardboard. Okay, pausing the video to grab cardboard. All right. So here it is. This is the best I had. So 30-degree, 50-degree, and up there is the 100-degree. So I guess what I was saying is when you get, of course, now I just need a blank sheet of paper. When you get a blank sheet of paper and you just draw a line, and I'll draw a line in kind of thick Sharpie pen to illustrate this idea. Okay. So here's just a line on a sheet of paper. Take your new measuring device, which is this one, and you can set that anywhere you want. So I can set it right on here and I can draw a 30-degree angle. I could rotate that shape and draw a 50-degree angle. Okay. So I'm going to do both of those, a 30 and a 50, right? And then we'll kind of see, well, what does that mean for our shape? What did we just create? And again, I'm using thick Sharpie. If you're using just this pencil, it'll probably work a little bit better. But I'll let you be the judge of what works best for you. Okay. So there's those two. Grab my straight edge. And all I'm going to do is connect those two lines. So again, here comes the fun part is, okay. So what did I just draw? Going up, we know that one's 30. Then going all the way up, we know is 50. So there's 30 and 50. Okay. So what I was trying to say earlier is, and I mean, I did say earlier, but it's maybe wasn't quite as clear, is I've also then by doing this, I've created another angle at the top, and I wish I had another color pen, but I don't. So I guess I'll use my regular pen. So this small angle up here on top must be 20 degrees. This little one right here, because the big one's 50, this one's 30. So I was able to measure an exact 20-degree angle. So now with my measuring device, I could take that 20-degree angle. Do you see what I'm doing right there? And I could put the 50-degree angle next to it like this and draw another line coming straight up. And that would give me a 20 plus a 50. That's a 70-degree angle. Okay. I could also take the 30-degree angle and start from that 30-degree line that I already had and build another 30-degree angle. So again, together those would be 60. But because I had 60 plus, there's a 50 right here, the difference between those would be 10. And that means I've actually created a perfect 10-degree angle. Now I'm going to go ahead and draw that on here so you can kind of see what that looks like. But this is the idea of this kind of problem, is to kind of say, well, what could you do? Again, a little bit of thinking outside the box, not going to lie. And so what could you do? Because sometimes people are like, all I can do is measure a 30 and a 50. And it turns out, no, actually you don't. You could measure more than that. Okay. So I'm going to write on here the two 30-degree angles that got me to this point. Okay. So you'll see them here. They look very similar. So here's a 30-degree right here, and there's a 30-degree up here. Okay, those are exactly the same size. Now you'll notice one of them right here, that was 20 degrees, right? Well, 30 plus 30, right? That's 60. I know 20 right there, so I actually have able to create another angle. So the beauty of this is that you could then use that 30-degree to continue and say, okay, well, what else could I make? Now, it actually looks like as I was creating this very, very quickly without a protractor, because all my protractors are at school and I'm at home right now. So it looks like this 50 might be just a little bit smaller than 50. So it might actually be more like in the 45 range. So the one I drew is supposed to be a 20 and a 10. They actually look pretty similar. So if you actually use a protractor on this, it'll make this angle just a little bit bigger, I anticipate. But that's the idea. So just with this, then I can come back now that I've got a 10, right? I could put a 10 with my 30, my small one, line those up, and now I've got an exact 40-degree angle because I can measure that out. So anyway, that's kind of the fun idea. And again, if you look here, here's the 50, which is kind of this big one here. So if I take my 30, put my 30 down here going down, I'd have a 30 plus a 50, which would get me an 80. So now I have exactly 80 degrees. I can even rotate the 100 around and put 100 with the 50, make 150 degrees, or put 100 with the 30, make 130 degrees. I could bring the 100 back over here. I have 120 degrees. So you have all these different angles you can actually measure, even though you only had a 30, a 50, and 100. So that's the big piece from that question. And the goal of this one was to try to say, actually, I can build any multiple of 10 degrees, and all I need is a triangle with a 30 and a 50 in it. It's pretty cool. So let's see. I think I answered the rest of that. Let's see here. How to measure a 40. Okay, there you go. So there's your 40. Yeah, so there's a couple different ways to do 40, like 50 minus 30. But if you built two 30s, that'd be 60, and you have 100. So build 100, and inside of it, build two 30s. And the difference there would have to be 40, because 30 plus 30 is 60, plus 40 gets you to 100. A couple different ways you could build 40 degrees, as you see. So anyway, that's the idea. All right, hope that helps. Enjoy the rest of the weekend. Off you go.